Alright, we're going to try this technology thing again. I didn't really fix anything, I just kind of rebooted a bunch of times, and we'll see if this works. Wow, 10 people. Yeah, I'm going to have to change my attendance policy because this isn't working. Thank you for being here, those who are here. Any questions? Good morning. Yeah, I should start giving extra credit for coming to class on time. Oh, that's cool. Yeah, I like teaching class, so that works well for me. So I sent an announcement out with a survey, and it looks like a bunch of people have taken the survey already. We're actually sending this out to we're spamming the whole engineering department, electrical engineering, computer science. We're just trying to get a feedback from people. If we had online opportunities for taking the program, to see if people would be interested in that. So so if you fill that out, thank you, I appreciate it. If not, if you have a chance, check out the announcement, and it's 2 questions, so it's not like an annoying survey that is like, you know, you're almost done and keeps asking you questions. So let me know what you see there. Well, we're doing an online program because we have no choice right now. But the question was, if you know, if and when we go back to in-person classes, is there a reason? Is there sufficient demand to offer some kind of online version, even though, you know, we're doing in person? So basically, that's just what we're exploring. That's a good algorithm for grade calculation. I like that. Unfortunately, if you set grade to A, it's going to be a 65 because that's the ASCII code of A. So you'd probably do better with a Z or maybe a lowercase something. All right, let's talk about tree efficiency. So, why do we care about trees, right? We've got linked lists. We can do lots of things with linked lists. We can do stacks and queues. Why are we bothering to talk about trees? And when we started talking about trees, we had this sort of, you know, kind of hand-wavy notion of order of complexity of operations. And the hope was that we could restore the log n behavior that we get with a sorted array, which was where we could, you know, hop into the middle of the array to search for something and then cut our list in half each time. And this is the ideal behavior for a tree. So imagine a tree, and I'm going to make a nice fluffy tree here where, you know, the end of it where the leaves are is like completely filled. And let's suppose we're searching for something in this tree. So first of all, how many nodes are in here? 1, 2, 4, 8. So we've got 15 nodes total. So 15 pieces of data. And we want to find, you know, some particular piece of data or determine that it's not stored in there. What's the maximum number of operations that we're going to have to do with this particular tree to, say, search for a number? What's the maximum number of things we're going to have to check to look for our number n in this case? Well, for this particular tree, You're right, but let's just go a little simpler here. Maximum number of checks we're going to have to do is 4, which is log n. So we have to check the root, and if we find it, we're done. But if we don't, right, based on our comparison, we'll check either this node or that node. And based on our results of that comparison, we'll move to either, you know, this node, this node, this node, or this node. And based on the results of that, we'll end up checking one of these 8 nodes. And if we find it, we're done. If we don't find it, we're done. So worst case, we've got 1, 2, 3, 4 operations that we had to do. And if we had 31 nodes and our tree was still nice and fluffy, it would look like this. And now the maximum number of checks goes up by 1. It goes up by 1 because, you know, we might have to go down 1 extra level after we get to these 8 nodes. We might have to search 1 level deeper. So it's basically, let me call this M so we don't get confused. It's basically, you know, if you have n nodes, it's log n checks. And this is what's so nice about binary trees. We can double the number of nodes. We could go up to a little more than double. We could have 63 nodes in this tree, and all it's going to do is add 1 more level, which means our number of checks will go up from 5 to 6. So each time we add another level, we double the amount of stuff in the tree. Right? So this log n is really nice. It's a really good characteristic for performance. All right. So so some terminology. So we can talk about the depth of a node. And the depth is the number of steps from the root to that node. So let me write some of these out. The depth of a node equals the number of steps from the root to the node. So this node right here, how many steps do I have to take to get here from the root? 1. So that's a depth of 1. And this node's also going to have a depth of 1. These nodes down here will have a depth of 2. Let me get rid of these so they don't confuse us. Why does this node have a depth of 2? Because from the root we do 1, 2 hops. This node we do 1, 2 hops. This node we do 1 and 2 to get there. So the root has a depth of 0. Because you don't have to follow any links to get from the root to the root. So the root has a depth of 0. Alright, so depth is, you know, start from a node, 1, 2, 3, 4 hops to get down here. So this layer has a depth equal 4. Alright, so that's one definition, the depth of a node. The height of a tree is the depth of the deepest node. So in this case, you know, my deepest nodes all have a depth of 4, so the height of this tree would be 4. And there's a special note. So a tree just consisting of one node, which is the root, that's going to have a height of 0, right? Why? Because there's a single node and the depth of that node is 0. So the depth of the deepest node is 0. But the height of a null tree is -1. It's like 0 factorial. It's equal to 1, not because it makes any sense, but because it makes lots of things work. So the height of a null tree is considered to be -1. That's just something we just need to know. Yeah, it's pretty cute. So with trees that aren't, you know, all nice and fluffy, this gets a little more interesting. So what is the height of this tree? Good. That's a height of 3. How do we know? Well, let's write down the depth of each node. And, you know, each node has a depth, but if I draw my tree relatively neatly so that all these nodes that are at the same level, you know, are next to each other, I can kind of, you know, cheat and say everything here has a depth of 1, everything here is a depth of 2, everything here is 3. So the deepest node is 3. That's the height of the tree. What would the Charlie Brown Christmas tree look like? Maybe something like that. So what's the height of this tree? So if we just look at the depth, 0, 1, 2, 3, 4, 5, 6. So that one had a height of 3. This one has a height of 6. All right, got the idea? Now here's the thing. So the maximum number of nodes in a tree of height h is, I don't know what it is. We gotta figure it out. So if your height is 0, then you have 1 node. If your height is 1, then you have 3 nodes. If your height is 2, then you have 7 nodes. So I think it's something like 2 to the height plus 1 minus 1. That seems plausible. So height of 2, right? So over here we had a tree with height 4 that should be able to contain, best case, 2 to the 5th is 32 minus 1 is 31 nodes. To the h plus 1 minus 1, yeah, to the quantity h plus 1. Yep, that one. We can prove that, by the way. We're not going to do that in here, but how would we prove that if we felt like we had to prove it? If you've taken CSE215, what's the two-word answer? Mathematical induction, thank you. Yeah, the really, really straightforward mathematical induction proof to show that this is always the case. And, you know, we just did a couple of base cases here. And then basically you just show that, you know, if you increase the height by 1, well, you add an extra 2 to something number of nodes, and if you work it in the formula, you can show that'll hold. Yay for math. All right, so here's the thing. Here we had a tree of height 6, right? Well, if the height is 6, we could have 2 to the 7th minus 1, 127 nodes. 2, 3, 4, 5, 6, 7, 8, 9, but we only had 9 nodes. So this is why it's a Charlie Brown Christmas tree, right? It's high enough that we could store, you know, a lot of nodes. You could have a lot of pine needles in there to hang a lot of ornaments, right? But this is a very sparse tree. It only has, you know, a few nodes here and there. And you know, that's bad for a Christmas tree, but it's also really bad for search efficiency. Because, you know, what this means is we're doing potentially as much work to find 1 out of 9 things as we could be doing to find 1 out of 127 things. And if we only have 9 pieces of data, and our tree looked like that, that only has a height of 3. So worst case, it's going to take us 3 comparisons to find something in there. But here, you know, it could take us 6 comparisons. So this is potentially twice as fast for the same amount of information. And the even more pathological situation for 9 pieces of data would be something like this. And so here, this is a 1, 2, 3, 4, 5, 6, 7, 8. Here the height is equal to 8. And it's going to take us 8 operations, worst case, to find what we're looking for. All right, so what's the moral of the story here? We would like our trees, as much as possible, to look, you know, more like this. I'm frozen. Yeah, make fluffy trees. That's the moral of the story. We'd like our trees to look like this or this. We certainly don't want them to look like this. And really, you know, yeah, shorter is better, because the height of the tree tells you how much work you have to do to find something. You have to go boink, 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 right? And if it's all, like, you know, short, then you have fewer hops. If it's all spread out like this, then you might have a lot of hops. So trees are a really efficient data structure. They get this log n behavior, provided they're nice and fluffy. So we need to understand this fluffiness. So the fluffiness of a tree is called its balance. All right, so the degree to which it is full, that's called the balance of the tree. And the ideal fill in one level before going deeper. So when I try to draw balanced trees during lecture, what do? Well, I start from top to bottom. And I kind of fill in, you know, each level from left to right, and then I go down. Now, you know, this is still a balanced tree. There's no way we could have this node anywhere else that would be better, right? At this point, we had 7 nodes. The tree was perfectly, you know, complete. If we want to add an 8th node, well, it's going to have to go off of one of these nodes, and it's not going to be, you know, a perfect-looking tree, but it's still considered balanced. And even if I have another node over here, that's still considered balanced, right? I can't put that node over here unless it makes sense. But if I start, you know, putting other nodes at a deeper level before I fill in this level, then I'm probably getting unbalanced. And we're going to analyze, you know, the balance of trees, but we're not going to worry about restoring balance for a little while. That's a very different set of algorithms we're going to have to talk about. But for now, we at least want to be able to analyze a tree and know how close is it to this ideal balance. So we have this notion of fluffiness or balance. So let me give you a definition. A tree T is balanced if one of 2 things is true. One, the tree is null. Nothing in the tree at all. We consider that to be balanced. Or all 3 of these statements are true. Statement 1. The height of the left and right subtrees are within 1 of each other. So the absolute value of the height of the left subtree minus the height of the right subtree is less than or equal to 1. And that just kind of makes sense because you know, that doesn't feel like it should be a balanced tree. And so if we look at the left subtree, right, that's got a height of 2. And if you look at the right subtree, that's got a height of 0. So since those differ by more than 1, right there we know the tree is not balanced. So that's the first of 3 criteria. The height of the left and right subtree have to be within 1 of each other. Everybody good on that? And I'm doing t dot left instead of t arrow left because I'm just doing pseudocode here. Alright, the other 2 criteria are where life gets really fun. The other 2 criteria is that the left subtree must be balanced and the right subtree must be balanced. So I just did something here, which might make you smile or might annoy you or might just confuse you. I'm giving you a definition for a tree to be balanced, and in that definition I'm using the notion of a tree being balanced. That's okay. We're going to do this a lot. So a tree is balanced if it's null or if all 3 of these statements are true. The left and right subtrees have heights that are almost the same, and the left and right subtrees are balanced themselves. So yeah, it's really about height checking. All right, we can do this without too much trouble. So let's look at an example tree. So let's suppose this is our tree T, and we want to know if it's balanced. Well, is it null? No. So we need three things to be true. We need the left and right subtrees to have similar heights, and they each need to be balanced. So let me draw pictures of these. So T left looks like this, and T right just looks like this. All right, so the height of this is 1, the height of this is 0. So they have heights that are within 1, so this criteria is satisfied. We need to know if these left and right subtrees are balanced. All right, so I'm going to put this aside for a moment. I'm actually saving it on my stack. And I'm going to just look at a different problem. Suppose this is my tree, and I want to know if it's balanced. So the left child is null. The right child is null. So the height is -1, the height is -1. So the heights are within 1 of each other. So that's good. Is the left child balanced? And is the right child balanced? What do you think? Is this tree balanced? Yes. Why? Because a tree is balanced if it's null. So this is balanced, and this is balanced, and the heights are within 1, and so therefore this is a balanced tree. All right, I'm going to go back to where I was, and one of the questions I had to satisfy was T right balanced, and the answer is yes. We just showed that that's balanced. We still need to know if this tree is balanced. So let me go to a different question. And say, is this balanced? Well, the left subtree is just this single node, and the right subtree is null. This has a height of 0, this has a height of -1. 0 and -1 are within 1 of each other. So this step is satisfied. So now we need to know, is this balanced? And is this balanced? Well, how do we know if a tree with a single node is balanced? Well, we're going to do all of this again. Oh, don't freeze now, man. The stack's not that deep. This is what happens in your computer too. If you try to do this too many levels down, your CPU will totally freak out, and then your hand will be frozen forever. There we go. All right, so we want to know if this tree is balanced. That's what the left subtree looks like. That's the right subtree. Man, I can't think of a good reason why I'd be able to lecture for 30 minutes and then all of a sudden things would start lagging. Other than Zoom and my screen recorder are sucking up resources. Yeah, killing all my Google processes yesterday did not seem to help. I just like doing it because there's 15 processes running. Alright, we will make quick work of this. Let's see if this works. Oh, it's not going to work. Alright, give me a minute here. I can kill them. Alt F4 is what I've been using for a lot of this. Could use paint. It could hold the paper in front of my face. So that would work. I should just use my chalkboard. I have a little chalkboard hanging on the wall. That would be kind of cute. And I know how this is gonna go. Yep. Alright, so I gotta kill my camera. And then I gotta do this. Alright, we'll try this. If it hangs, I'll go back to cheese. Alright, fleeing the Cylon tyranny. We are trying to determine if this is a balanced tree. So we look at the left child and the right child. The left child has a height of 0, right child has a height of -1. Those are within 1 of each other. So that criteria is satisfied. And now we need to know, are the left and right children balanced? Well, the left child is a single node, and how do we know if that's balanced? We do something like this, which we already did, right? We had a single node, the heights agree, the left and right children are balanced. So yes, this is balanced, so the answer here is yes. And then we ask, is this right subtree balanced? Well, the right subtree is null, and our definition says a tree is balanced if it's null. So yes. Therefore, this tree, since the heights are within 1 and the left and right subtrees are balanced, this is balanced. So that's the answer to our question here. Is this tree balanced? Yes. And now we've decided the left and right subtrees have a height within 1 and both of those subtrees are balanced. So yes, this is balanced. Alright, that's all the legwork that we had to do to ascertain whether this tree was balanced. But really, it's just this one definition. If the tree is null, it's balanced. If the heights differ by less than or equal to 1 and the left and right subtrees are balanced, it's balanced. Otherwise, it's not. And you can see how much flipping back and forth of papers and rebooting of computers and stuff we have to do to apply this algorithm. But this algorithm is really, really short, right? I mean, see if your tree is null, that's one statement, right? See if the heights differ by more than 1, that's one statement. And the trick is telling if the left and right subtrees are balanced, right? So here's what we're going to do. Still sort of pseudocode. Let's figure out if a tree is balanced. So if the tree is null, let's return 1. If the absolute value of the difference in the heights is bigger than 1, we can return a 0 and say it's not balanced. I am frozen. At least I understand the nature of the beast now. Yeah, it was going for a little while. So if the difference in the heights is bigger than 1, we can stop right there and say it's not balanced. Okay, how do we know if the left subtree is balanced? I'm going to do this. That's our whole balance algorithm. I could actually do it in fewer lines than that. I could actually do it in like 2 lines. So if the tree is null, it's balanced. If the heights differ by more than 1, it's not balanced. If the left tree is balanced and the right tree is balanced, and the heights differed by less than or equal to 1, and it wasn't null, return 1. It's balanced. Otherwise, it's not balanced. That's it. That works. We can code this in C and it will actually work. And this fact that the balance function is calling the balance function is not a problem at all. Okay? And this is recursion. And recursion is really just, the idea of breaking a problem into subproblems. Telling if a tree is balanced by saying, well, are both sides balanced? And do they have similar heights? If they do, then I'll call the whole tree balanced. That's all we're doing here. All right, questions about this? So we can use this idea for a lot of things that we're going to do with trees. Let me show you a recursive print function. And we'll definitely go into these more deeply next week. But we've got a few minutes here before, Friday exam, weekend, Monday holiday, so good number of days break. So let's just look at some examples. Suppose we want to print the contents of a tree, and we want to print with this in order traversal. So here's T. And we'd like to, come out with 5, 10, 11, 20, 27, 30, 33. So this left node right traversal, I said we could think of this as basically printing all the data in the left subtree of T, and then printing the root of T, and then printing all the data in the right subtree. Well, we can put that together into code pretty easily. If T is null, we'll just return. There's nothing to print. That's easy. This is a base case. Base cases are usually not too taxing. So if the tree is null, just return. Nothing to see here. Otherwise, what do we want to do? We want to print everything that's in the left subtree. And then we want to print the root node's data. And then we want to print everything that's in the right subtree. And that's it. 4-line print function. And it's a little, dare I say, inconceivable that these 4 lines of code, which don't really do anything about, go to the left and go to the left until you can't go any further, and then pop up and go to the right and go to the left, and all the stuff that we did yesterday in our algorithm is missing from here. Right? This is trivial. Right? Print the left subtree, print the root, print the right subtree. That's, our definition of how we want to do left node right traversal. But this will actually produce 5, 10, 11, 20, 27, 30, 33. And that's pretty cool. Now, when we do this, I was planning to show this in code, and I didn't get it spun up in time. But we'll definitely do this in code on Tuesday. When you're doing recursion right, it always has this feeling that you're cheating, right? It always feels like, this can't be, this simple. Where's the work actually getting done? In some sense, the only thing that's actually doing any work is right here. It's this base case. The only thing that's ever printing anything, though, is... Sorry, this should be like a printf, This is where we actually call, the printf function and print out this integer. But these are, recursive calls to our function. So this is where we actually print something. But this process of calling ourselves recursively will cause all of that logic that we saw in the algorithm yesterday to come into play. And this will have the effect of, right, if we start off with a tree T and it's not null, we're going to call the same function with the left subtree. And when we do that, we're going to call the same function with the left subtree, and we're going to call the same function with the left subtree of that. This part of the logic is the effect of moving down left as far as you possibly can. And guess what? Each time that we make a call, what happens? Our current context, including our variables, are pushed on the stack. So the node that we're at, the root of the tree, is being saved on the stack. And then we're hopping into the next level by going left. And when we get to the point where we can't go any further, that's when we've called print with t being null. And since it's null, we'll return and we'll print out the root data. All right, so this is where stuff starts to turn into something different. Up to this point, the code we've been writing is basically a series of steps. There's loops and things like that. But this is really where we start kind of doing a different kind of programming. And a certain measure of faith is needed to write recursive code. You really have to believe that my function, when I'm done with it, is going to print out everything in this tree. And if I believe that, then I believe this function will work. But the only way I know that this function is going to work is if I believe that this function is going to work. And this is mathematical induction. The reason that my print function works for this original tree is because it also works for these slightly smaller trees. If I know my print function will succeed in printing this tree, and I know my print function will succeed in printing this tree, I can absolutely prove to you it will succeed in printing this tree. Why? Because what does the function do? It calls print on a left child, so we'll print these nodes in the correct order. And then it prints out the root nodes data, which should be right in the middle. And then it will print all the stuff in the right subtree in the correct order. Takes deep faith. Gotta have faith. All right, so we're going to kind of shift gears for the rest of this course and for a lot of 223, and we're going to start thinking more about recursive approaches to things. And recursive code generally is easier to write and it's easier to read. It's more work on the computer, and sometimes that's a problem. For trees, it's not a problem because the amount of times that we're going to call ourselves is limited. It's limited by what? It's limited by the height of the tree. Because if I call this algorithm on a left or right subtree, each time I do that, the tree I have is shorter. And if my original tree had a height of 20, after 20 of these recursive calls, I'm going to be down to a tree that's null. I'm going to start popping my head out of the rabbit hole. Oh, we should do a computer science cult. We got to come up with a good name for it. Something no one will ever think. All right, so that's a preview of recursion and recursive programming. And like I say, Tuesday we'll go through this and we'll start looking at it with some code, and we'll have a few weeks of exposure to this to get more and more comfortable with it, and eventually it will become second nature. Takes a little while to get there, but we'll get there for sure. All right, I will see you. Have a good one. Enjoy the snow if it comes. Try not to miss your midterm tomorrow, and I will see you then.